Welcome to this lecture series in group theory. We are starting a new module which will be about special kinds of group actions. These are very useful in proving very non-trivial things. Today's lecture will be relatively simple. What we will discuss is regular action. And before that, let us look at what we need. And what we need is only the definition of a group action. So as we saw, a group action can be thought of as two different things. One perspective is it can be thought of as a map from G cross X to X, which has two properties. It says that phi e comma x is x for all x, and phi g comma phi h comma x is phi gh comma x, again for all group elements g and h and for all x in the set x. So we said that instead of writing it this way, instead of writing phi g comma x, we write g dot x with the understanding that the phi is hidden from notation for simplicity. So yeah, that is one perspective. The other perspective is that you can think of as a group action as a group homomorphism from G to the symmetric group of X or the permutation group of X. And one can pass from one to the other. We discussed that. So this is all we need to know for this lecture. So here is the definition of the regular action. So fix a group G. Then we can define an action of G on itself as follows. How do we do this? Define a map which takes G comma X to Gx. Or if you want to suppress the notation capital phi, all we are saying is that G dot X is defined as Gx. Of course, this has to be understood. So this dot refers to, the map phi. Basically, G dot X means phi of G comma X. And this means the group operation between G and X. So X is also a member of G. The set X here is the same as the group G. And therefore, it is legitimate to just take the group product of G and X. So that's what this thing is. And let's just see why this is an action. And that is very simple. So what is G dot E? It is by definition, what am I writing? E dot X. This is by definition EX, the group product of E and X, which is, of course, X because E is the identity. And this is true for all group members. And the second thing we need to check is that G dot H dot X. What is this? This is equal to G dot HX, the group product of H and X. And this is the group product of G and HX. But by associativity of group multiplication or the group operation, this is equal to that. And therefore, and of course, this is equal to GH dot X. So this thing is equal to that thing for all GH in the group G and X in the group G, which, so so this action is called the regular action of G on itself. It's called the left regular action, but I will suppress that. All right, so that's just a definition. And it has a very nice corollary, which is called Cayley's theorem. Cayley's theorem says that every group can be thought of as a subgroup of some permutation group, or in other words, every group can be embedded in some permutation group. This was given as an exercise earlier, but now we will give a proof of it. Let me write down more precisely what this means. It says that what it is trying to say is that if G is a group, then there is a set X and an injective group homomorphism Is that a correct spelling of homomorphism? There is a homom, so too many oms, but anyway. Group homomorphism from, injective group homomorphism from G to the permutation group of X. Right, so This is the precise sentence which has been stated in this way. This sounds more meaningful. This sounds like some technical garbage. All right. So that is what we want to prove, and the proof is very simple. Let x equals g, and consider the regular action. So this is the regular action. And since we have an action of g on g, what we get is a homomorphism from this to sim x, or let me just write that as sim g. So we get a group homomorphism from g to that, and we claim that this is injective. So claim phi is injective. All right. So first of all, what is the image of g? So let's write. So fix. Yeah. So before we make that claim, let's do something else. So for g in g, write phi sub g to mean phi of g. So that's just a notation thing, and note that. So yeah, note that phi g of x is gx for all x. So this is immediate from the dictionary between the two perspectives of group action. The way we defined the regular action in the previous slide translates to exactly this, that if you take the image of an element g under this homomorphism, it behaves this way. And I mean, this is the permutation of g induced by the group element g. That is what we are saying. So that's a very simple observation, or whatever you want to call it. And now we claim that phi is injective. So since phi is a group homomorphism, we just need to find out the kernel of phi. So this is the proof of the claim. Let g be in the kernel of phi. Then phi g is the identity permutation. Identity of sim g, which implies phi g of x equals x for all x, which implies gx equals x for all x. In particular, this means g dot e, or ge equals e, which implies g equals e. And therefore, the kernel of phi is trivial. So what we have shown is that this thing is actually equal to the trivial subgroup, and therefore phi is injective. So that's it. That finishes the proof. This is what we wanted to show. We wanted to find a set x such that you can embed g inside the permutation group of x, and that's what we just did. So the regular action immediately leads to the proof of Cayley's theorem. One could have directly given this proof. You don't really need the notion of group actions. You could have just directly defined this map phi in this fashion, that the image of g behaves this way. Just verify that this is a group homomorphism and show that it is injective, and that's it. That was pretty much the proof that was hinted in an exercise, but here we look at it from the perspective of group actions. So that's it. This is about what I want to discuss in this lecture. We will look at an application of regular representation in subsequent lectures, and we will obviously mix and match with what we have learned. We will use other things simultaneously. So that is when we can prove really interesting things. And with that, let me end this lecture. And as usual, like, comment, share, subscribe. I will see you next time.